Hello students, welcome to the fifth session. In today's session we will be discussing briefly about combination of cells, Kirchoff's laws, and some of the applications of Kirchoff's laws, especially meter gates, and possibly we will discuss briefly about potentiometer as well. Okay, so let us meet at 2:30 hours. 2:30. Yes, right. Okay, fine. So I hope you're getting the voice clearly. At 3 o'clock. Okay, so last class we have discussed about combination of resistors. Cells. We are discussing some questions about combination of resistors. So let us see briefly the two questions. Then we will go with the combination of cells. Okay. One small question. Find effective resistance between A and B. Find effective resistance between A and B. This is terminal A, and here two resistors are connected between this A and B, and along with this, few more resistors are connected in a different fashion. Like from here, there is a resistor is connected, and here one more, and these two are points are connected along with resistor to B, and similarly there is another resistor here, one more, and here one more is connected resistor combined joined, and similarly here along this diagonal one resistor here and it is joined here, the one more resistor here is joined here. Here similarly you can redraw this carefully so that it will be convenient to draw like this, and it should be looks like there's a proper diagonal. Okay? You have to take care of while drawing it. It will be like this. So you can redraw to represent the scene properly. So that it is looking like this. Okay. So how many resistors are there? Right. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. 12. So these all resistors are having same resistance. Identical resistors. These are all. So it is a triple R, and this is another triple R. This is another triple R. This is another triple R. Right. All are identical resistors. So how to find effective resistance between A and B is the question. Another question is I will give you an idea of hint for this. You can try this one, another one. So here we have two resistors connected in one arm of, let us say, a square or rectangle, right? In this fashion, and here also the same fashion. In the same fashion. Here, from the midpoints of these. By joining them, we have connected each resistor here like this. And here one more resistor, so that these are all identical resistors. This is marked as point A, this is marked as point B. Okay, and we are asked to find here resistance between A and B, provided these are all identical resistors, identical, and these are all identical. So this is yes, also have the same resistance. What is the effective resistance between A and B is the question. Okay, so while finding this, while working with this kind of questions, we can use some different symmetry relations. We have to use some symmetry relations. Usually we come across two kinds of symmetry relations. One is mirror symmetry and another is folding symmetry. Mirror symmetry and folding symmetry. If you are asked to find the resistance between 2 points, so that if there is a same arrangement above and below that particular line, a symmetrical line, if you draw across this AB, if there is exactly similar kind of section above and below provided, and those corresponding resistors are also having similar kind of values, something like so this is N and this is R and this is NR, R and 2R, like this kind of combination should be there. In such cases you can use folding symmetry. Folding symmetry. Otherwise you can use mirror symmetry. So here you can apply mirror symmetry or folding symmetry also. They are all identical resistors. So according to mirror symmetry, if you see here, if you draw a line here, about this line, if you see exactly how many resistors are here, this part looks like the mirror image of this. This is mirror image of this. If you take one mirror, so the set of resistors from you will see this will be representing the same. So likewise, these will be like. In such case, you can apply mirror symmetry. But here, as exactly same resistors are there, how many resistors are there, and top section, same number of resistors are there in bottom section, so you can use folding symmetry. Here, you can see how to use mirror and folding symmetry in both cases. According to the folding symmetry, so this is point A, let us say this is point X, or you can write AB, PQ, or this we are using some different symbols, right? So resistance symbol is R, so you can use this is M, this is M, both are having same potential. Then if you come somewhere here, here we have one resistor, like this junction, this is M, this is N, this is M. Do you understand? Now, what you have to understand, what you have to do the next step is, you have to fold these so that this and this will have the same potential. Are you following this? This and this will have the same potential means this resistor is between A and M, this also will be between A and M. So these two are said to be in parallel. In parallel. Same way, this is here. Let us mark this center point is some more. This resistor is between O and M. This is also between O and M. These two are treated to be what you call parallel to one another. Got it? So similarly, these two and these two and these two, this, and you can say because they are folding like this. They are folding like this. So you can say these will be in series, of course. So if you redraw this, you can get one relation. This is point A. Then this resistor, you have to take these two resistors as these R and R, and this resistor you can take this as R by 2. The following, and so these two. So these two we have taken replaced as R by 2. Then these two can be replaced here from this point to this point, R by 2. And then, so if you, this is between M and N, that is also between M and N, so you can take this as R by 2. Then again, these two between O and N can replace this here with this is one point with R by 2. And here another one is R by 2. This is your B. So now, this is what we call first step of reducing. Next point is, if you analyze, if you imagine an imaginary battery between A and B, so a battery between A and B, the current comes here, this will divide between these two sections. Once it is divided, let us say this is I, this is I1, this is I2, at the end point, the same amount of current should flow. That means this I1, whatever this is I2, this has to reach here, and whatever I1 has gone here, this has to come here as I1 by symmetry. Is it clear? I'm following or not? If I2 has to come here and I1 has to come here, means once I1 come here, it has to divide. It has to divide at this junction. After dividing, after coming here, so let us say this is I1, I2, I3, I4, let us say I3, I4, and these two again has to join here to give, what is this? I1. So that then only I1 will go here. These two will combine as two. That means this current anyway will come across this. This current has to come across this. It shouldn't divide here. That means we have to consider that there is no connection here. That means this current should come as days. That means we have to detach this connection. We have to assume that there is no connection between these 2 points. So then it's the same continuity process here. Then we can understand this. These two are in series. So R by 2 plus R by 2 will give you R. Then R is in parallel with R by 2. Reduce it further. Then this and effective of this and this will be in series. Reduce this 2 with 1. Then these two are in series. Reduce this with 1. Then you will find out the effective resistance. Got it? Yes? How can you do this in the next step? The next step? So you can see this is, just do yourself quickly. So this is, and these two you can replace with 1. This is R, right? When we are folding, this is nothing to do with any other, what you call, parallel resistor. So these two are R plus R becomes 2R. This is 2R. Yes? Here, this 2 becomes 2R. Then what about these two? This part, R by 2 plus R by 2, R is in parallel with R by 2. What is the effective? R1, R2 by R1 plus R2. So these are R by 2 into R by R plus R by 2 is 3R by 2. 3R by 2. So you can write it as, what you can write? 2 to cancel, R cancel, it is R by 3. This is R by 3. Check it quickly, check it yourself. So the effective of these all will become R by 3. R by 3 or R by 2? Check it. So R into R by 2 plus R by 2. R plus R by 2 how much? R plus R by 2. 2R plus R. 3R by 2. 3R by 2. Yes, here then it is 2 to cancel. 1 R gets cancelled. R by 3. Yes, I will R by 2. Now R by 2, R by 3 and R by 2 are in series. Are in series. So if you add them, because you can replace this as this is R by 2 and this is R by 3 and this is R by 2. They are in series. So if whatever current coming here, the same current passes through this means all the 3 are in series, add them directly. We get R by 2 plus R by 2, R plus R by 3, R plus R by 3. R plus R by 3 is equal to 3R plus R, 4R by 3. So the effective of all these will give you how much? 4R by 3 or 4 by 3R. That 4 by 3R and 2R are in parallel between A and B. So effective resistance between A and B is what? Now I can say this is A. So I can draw somewhere here. Of course, you can erase this. So this is 2R. And what is the effect of this? What is the effect of all these resistors? 4R by 3. This is B. So these two resistors are in parallel between A and B. That is the effective resistance. What is the effective resistance between those? 2R and R, 4R by 3. Parallel. Do the calculation part. So what is that? How much? 2R to 4R by 3. 2R into 4R by 3 divided by 2R plus 4R by 3. R1 R2 by R1 plus R2. So simplifying. This will become 6 plus 4, 10. Huh? So it is, you can write it as 2R into 4R by 3 by 6 plus 4, 10. 10R by 3. Got it? 3 cancel. R gets cancelled. 2 1s, 2 5s. 4 by 5R. 1 R is there, right? Is equal to 4 by 5R. Or 4R by 5 is RAB. So it is RAB is equal to how much? 4R by 5. Got it? Check whether you have did calculations properly or not. If you do any small mistakes, then you will go wrong. So if I do any what you call calculation mistakes, correct it, and this is the procedure you have to do. Procedure is this. So based on this you have to simplify. Okay. Same way here also. What you have to understand, between A and B you want. So draw a line between A and B. If you observe here, so how it looks like if you keep one mirror here, it exactly like the same way. So if you connect a battery between A and B, current comes here and it divides into 3. Oh, so here into this many. So all this, so I1, I2, I3, I4, I5. So I1, I2, I3, I4 up to I5. These are all will combine again here. So this I1 should have come as this here. This I2 should come as this here. This should come as this. This should come as this. This should come as this. So then another, instead of like using what you call folding symmetry, after folding symmetry you come across this, right? This directly can take the step the other way. What is that is, as this current is coming as it is, we can this break the connection here and assume that these two are connected directly. So these two are in series, and obviously then these 4 are in series, and similarly break this connection. So these two are in series and these 4 are in series. Reduce them. So this is R plus R. This is 2R, 4R, 2R, 4R, R. Oh, these are all in parallel. What is effective resistance? Got it? Find out what is effective resistance then within one step. If you practice, then you can do within even a minute. Simple. You do it fast. What is this? 4R parallel. Right? Between A and B. Between A and B, you can, for convenience, you can take this is A, this is B here. We have R here, R, then this is 2R, parallel, right? So parallel combination of these two, if you reduce, what do you get? This is R, 2R, 2R by 2. So R, and this is 4R by 2. What do you get? 2R. 4R by 2 is 2R. So R and 2R, 2R, these are in parallel. So this will give you what? R by 2. And this is in parallel with 2R. So R by 2 into 2R by R by 2 plus 2R. What is that? 2R into R by 2 by 2R plus R by 2 is equal to 2R into R by 2 by 2 into 2, 4R plus R, 5R by 2 cancel, this R cancel, 2R by 5. 2R by 5 is the effective resistance. Got it? This is how you have to work out with the calculation of effective resistance. Calculation of effective resistance. I think that part is not visible here for this online guys. Right. Okay. So can I erase this? Finish everyone? Practice, then only you can remember, you can understand. Some steps if you are confusing also, if you copy and practice, then it will become clear. Right. Yes? Yes. Okay. Is done everyone? Next, let us see briefly about combination of cells. Combination of cells. Combination of cells. Combination of cells. So, the first one is series combination. Series combination. Combination of cells or grouping of cells. Series combination or series grouping. When cells are said to be connected in series. When cells are said to be connected in series. If two cells or two or more, n number of cells. If n number of cells are connected end to end, such that if same currents, especially actually you can say in case of resistors and capacitors, resistors, same current passes through all the resistors, and capacitors same charge should flow through all the resistors, right? But in case of cells, you have to say that if one end of the cell is connected to another end, so that the same net current is passing through net current. This may give some current, that may give some current, but same net current should pass through all the cells. Then those cells are said to be connected in series. So if these two are connected to an external resistor, its EMF is E1, internal resistance is R1, its EMF is E2, its internal resistance is R2. Then how to find effective EMF of this combination? Same as series combination of resistors or capacitors. Why we need this? To reduce the space, to save the space in circuit. So to understand that, you have to replace this with an identical circuit. We have a cell having equivalent EMF, equivalent internal resistance. If you connect this to an external resistor of resistance R, it will behave same way as that of the group of resistors. Okay. Now, what you can understand is, in this, the terminal potential difference, and hence terminal potential difference, and hence the currents. Same current may passes, but potential differences may be different if the internal resistances are different. So you can say in this case, as this is let us say it is V1, here it is V2, okay, across this. So potential difference across this, whatever the EMF, is equal to this. Or you can say, if you replace this, so if this is having effective potential V, then if a same current I is passing here, the potential difference across this is nothing but I into R. That is nothing but here I into R, if they are in series. Here you have to understand a little carefully. So by making use of the expression for terminal potential difference. Terminal potential difference of this is V1. If you take V1 is V1 minus IR1. So if it is I is coming across, if I is coming across, this will be E2 minus IR2. By taking these relations into consideration and on simplifying, we are not going to discuss everything step by step, but the final steps you will get. And for parallel combination, I will give it clearly because this is very simple. So I would like to give directly. E equivalent will be equal to E1 plus E2 in this case, and R equivalent is equal to R1 plus R2. So our main important requirement, aim of this condition is how to find effective EMF. So in case of two cells are connected in this fashion, effective EMF or equivalent EMF of the two cells is E equal to E1. This condition is also called as, if two cells are connected like this, where it is said to be connected in supporting manner, means current due to this and current due to this will add up. So we call them as then supporting manner. Whereas if they are reversible polarity, they are said to be connected in opposing manner, not in supporting manner. Okay. So here, this is in case of two cells. Instead of two cells, if you have n number of cells. If you have n number of cells, then E equivalent simply you can say is equal to E1 plus E2 plus so on plus En. Similarly, R equivalent is equal to R1 plus R2 plus so on plus Rn. And if these n number of cells, are identical, means each cell is having same EMF E and same internal resistance R, then what will be the effective EMF for n identical cells? For n identical cells. E equivalent is equal to 2 cells means E plus E, 2E, 3 cells means 3E, and cells means n into E. Right? Similarly, R equivalent. R is, what is this R? Internal resistance. Equivalent internal resistance is N into R. What is N into R? That is what is, this is how we can find out this. Whereas in some cases, the questions may come like, if two cells are connected in series or n cells are connected in series, what should be current through the resistor? You may ask. What is the current through the resistor? Then simply you can say I is equal to, what is the general formula for current? What is that? V by R. From Ohm's law, I is equal to V by R. From Ohm's law, I is equal to V by R. So here we just modify that little bit and we take it as V is nothing but EMF. So you can say net EMF in the circuit by what is that? Total resistance in the circuit. Total resistance in the circuit. So whenever you say in a circuit what is current means net EMF by total resistance. You have to say net EMF by total resistance. What is net EMF in this? This one supporting manner. So EMFs will add up. Net EMF is nothing but equivalent EMF. So what is this? You can also say equivalent EMF or net EMF. It is equal to E1 plus E2 plus so on plus NE. If they are all identical, you can check it as NE. Okay? So if it is, they are having different EMFs, you have to add them and you just have to take. By R total is R equivalent means sum of all internal resistances plus external resistance also you have to take into consideration. External resistance also you have to take into consideration, right? So we can write that in this case it is equal to E equivalent by capital R plus R equivalent. That gives you current. So the E equivalent can be this or this in case of different cells, identical cells, this and this you have to take. That's it. Yes? Got it? So this is briefly about how to find current in a circuit which is having n number of cells in series. N number of cells in series. Got it? Next, if n cells are in parallel, have you copied these points? Everyone? Good? Next, write down parallel combination of cells. Parallel combination. Parallel combination of cells. Parallel combination. Then same way, when the cells are said to be connected in parallel, and how to find the effective EMF of parallel combination of n number of cells connected in n number of different cells connected in parallel and n identical cells connected in parallel. One point before discussing about parallel cells, one more point about series combination only. About series combination only. If you have n identical cells, for n identical cells, for n identical cells in series, for n identical cells in series, what is E equivalent? NE. R equivalent? N R. Yes, for n identical cells. Whereas, out of this n, if m cells polarities are reversed, or that can also be called as they are connected wrongly. So instead of connecting like this, like this, like this, like this, that is positive, negative, positive, negative, positive, negative. So if out of n cells, if m cells are connected in reverse order or wrongly, means like this, then another cell is connected like this, reverse. Alright? So if you have some 3 cells like this and 2 cells like this, then what is E equivalent EMF? What is E equivalent EMF? So in that case, write down here, and that is only if m out of n identical cells connected with the reverse polarity, with reverse polarity within bracket or wrongly connected, which both will say with reverse polarity, then E equivalent is equal to n minus 2m into E. Provided m should be, if you take this m should be less than, n should be greater than 2m. Greater than 2m means if this m is 10 cells are there, then m is some 2 cells are reversed. So 2 is this m, right? The cells which are reversed are connected wrongly. Twice 2 is 4. Total is 10. Out of 10, 4 is less than half of the cells, right? So that m should be less than that number. Then only you get you have to use this relation. Otherwise, you have to do in a different means like conventional method you have to use. That is E equivalent. Whereas R equivalent, if you connect all cells in the same manner or in opposing manner, the resistance will add up always. Resistance will add up. So you get this one. You get here one. So hence, what will be the current? What will be the current? I is equal to N minus 2M into E by what? N R plus capital R. If an external resistor is there in the circuit, only cells are given, then you can take NR only. That's it. Yes. If they are connected to an external resistor. Right, next, parallel combination of cells. Parallel combination of cells. Means it's a bit. Yes. Shall we get a lot of energy? Right. You have to. Then only here it will come to your. Okay. Fine. Next, parallel combination. When cells are simply connected in parallel, if positive terminal or higher potential of all the cells are connected at one point, and lower potentials of all cells are connected at another point, then they are said to be in parallel combination. For understanding purpose, let us consider only two cells. This is E1 having internal resistance R1. This is E2 having internal resistance R2. They are connected in parallel across an external resistor R. Then what should be the equivalent EMF, and hence what should be what do you call equivalent internal resistance. Equivalent internal resistance. The following. So when two cells are connected in parallel, the potential drop across this will be same. Potential drop across this will be same. That means here potential drop across this, or we can say terminal potential difference will be same as the potential difference across this. Whatever it is, potential drop is here, that will be the same potential drop difference will drop across this. So if the current I is passing here, potential difference across this will be taken as I. V is equal to R. V is equal to IR. Got it? So that will be the same as this. And now again, by taking the equations of potential difference of the two cells separately and equating them and simplifying, we get what is the effective potential or effective EMF and effective internal resistance. I will give you directly expressions here, but you have to remember that here potential difference is for this is given as if it is current if current I is flowing here. So this is I1 is giving I1, this is giving I2. This is combining and giving you I. Hence I1 plus I2 gives you I. I1 plus I2 will give you I. So here, you have to use the relation of I1. This is I1, and I1 for I1, potential difference across this is given by E1 minus I1 R1. Potential difference across this is E1 minus I1 R1. For this is E2 minus I2 R2. But both of these potential differences are same. Equating them, and after taking the what do you call it? Equivalent circuit conditions. That is, if you replace this with a single cell of equivalent EMF and equivalent orbital resistance, disconnected external resistor of resistance R, then you get the same results. By equating these conditions with that, then you get the E equivalent is equal to you can write E1 by you can also write it as simply. I will give you different ways of representing this. R equivalent E into E1 by R1 plus E2 by R2. One way of expressing this. Got it? This can also be expressed as for two cells. As the resistors are in parallel, R equivalent will be taken as R1 R2 by R1 plus R2. So this I am simplifying again. You can write as E1 R2 plus E2 R1 by R1 R2. This is R1 R2 by R1 plus R2. R1 R2 R1 get cancelled. You get E1 R2 plus E2 R1 by R1 plus R2. Because here R equivalent for parallel combination is R1 R2 by R1 plus R2. You want to write here. Because R here, that is E equivalent. And R equivalent is what? R equivalent is R1 R2 by R1 plus R2. Substitute this here. Or you can also write that 1 by R equivalent is equal to 1 by R1 plus 1 by R2 in parallel combination. Got it? This is only for two cells. This can also be expressed as E1 by R1 plus E2 by R2 divided by 1 by R equivalent also together. While especially the questions will give in this way also. So you have to be careful about representation of this. So don't confuse that this is the only correct way of representing. You can also express this as E equivalent is equal to E1 by R1 plus E2 by R2 whole divided by, this can be expressed as 1 by R equivalent. So R equivalent goes to numerator and it multiplies. Alright? That we also can express. So remember this way of representing. Next, for n number of cells. For n number of different cells. You will see then for n different cells we will verify. For n different cells. For n different cells. E equivalent can be expressed as from this. Let's start with this. From this we will say E1 by R1 plus E2 by R2 plus E3 by R3 plus so on plus En by Rn. Right? And this one is 1 by R equivalent. 1 by R equivalent is 1 by R1 plus 1 by R2 for 2 cells. For 3 cells, 1 by R1 plus 1 by R2 plus 1 by R2. 9 cells, 1 by R1 plus 1 by R2 plus 4 1 plus 1 by R1. So this is how we are going. So this you can write in short as sigma E1 by R1 plus E2 by R2 so on, that we can express as Ei by Ri, where I goes from 1 to n. That's numerator. Denominator 1 by R1 plus 1 by R2 plus 1 by R3 plus so on, that can be expressed as sigma 1 by Ri, where I goes from 1 to n. This will be directly enough for n cells. They are identical, you can take all are same. So n we can take accordingly for an identical cells. What do you get? Analytical cells. All i's are same. Then we will write E by 1 is equal to 1 to n. So E by R plus E by R plus E by R n times. So n E by n R. 3 by R. Yes. Yes or no? So here this is 1 by R n times. We give you n by R. N by R. So that R goes there and it divides with n. So either way you can. So you have to be carefully take this step especially without confusion. Right? This is how we can express what is the E equivalent in case of parallel combination. R equivalent is R equivalent is this. This is R equivalent. 1 by R plus 1 by R so on. So R equivalent in case of parallel combination is you can take better take it as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus so on plus 1 by Rn. R is written as sigma 1 by Ri, where I is equal to 1 to 2. That is R equivalent. Right? This is briefly about combination of cells in parallel, series and parallel. If you come across mixed grouping of cells, mixed grouping, so especially we consider identical cells only. If you consider cells are definitely enough, it will become more complex. So let us consider n identical cells connected in m rows. Then how to find the FFPMF? Mixed grouping of cells. Again, here also if you are asked to find what is the current and through the resistor, I will take that one. What is that? I is equal to E equivalent by R. Total resistance. So next, mixed combination or mixed grouping of resistors. Mixed grouping of resistors. Mixed grouping of not resistors, cells. Mixed grouping of cells. So what is mixed grouping is if you connect n number of cells. N number of cells. How many? 1, 2, 3 and so on up to n. And identical cells. All are having same EMF. In series. Like this, one more set if you have, one more set you have, like this, m sets if you have, this is one set, two sets, like this m sets. How many m sets if you have? That means if all these are connected, through an external resistor, of resistance R. Then what is the current through it and what is the effective EMF of this. What is the effective EMF here? What is the effective EMF or equivalent EMF? EMF of effective EMF of this you have to take. Then you have to replace all this with 1. You have to replace this all this with 1. So what is the effective EMF of all these? N into E. Yes? This is also N into E. N into E. So NE are connected n times in parallel. So if E are connected in parallel, M cells are connected in parallel, N cells connected in parallel, I have discussed it there. So, but here M cells we are taking. In such case, what we have to take is ME by here R. So you can say effective EMF is NE and equivalent resistance is NR. NR. Like that, here NE, NR. All these should be replaced with. All these should be replaced with NE with NR. Now, NEs are in parallel. How many? M such cells. So we can write this as, now we can here, sigma of this. Di by Ri. But I goes from 1 to M. 1 to M. So NE, how many times? M times. So into M everything. So NE by Ri. 1 by Ri. I can take that separately into 1 by Ri. Here 1 by Ri. Then it gets cancelled. So this gives you what you call A effective EMF. This gives you effective EMF. Got it? Directly I am giving you. So you have to understand. Otherwise, you can write it as NE into M by what is that? 1 by Re into 1 by Re, 1 by Ri divided by 1 by Ri. This 1 by Ri gets cancelled. So you can conclude that this is equal to M N into E. M N into E. This if you write step by step, then only you understand. Otherwise you can finish. So hence R equivalent anyway, R equivalent. So R, M number of resistors R's are in parallel, it is R by M. But NRs are in parallel, NR by M. You get NR by M. So here R equivalent is equal to NR by M. Very small r by M into R equivalent. That's it. Is it clear? And hence the total current should be I is equal to the resistor is equal to net EMF by total resistance. Net EMF is how much? MNE by total resistance is capital R plus this one. Capital R plus NR by M. Got it? So this points you have to remember about the group. What is it? Mixed grouping of cells. Mixed grouping of cells. This briefly about mixed grouping of cells. Now we can deal with the circuits having resistors and what you call cells combination. Resistors and cells combination. So let us work out few questions. After discussing what are Kirchoff's laws, then we will try to understand how to deal with such circuits. Next, write down subheading Kirchoff's laws. Kirchoff's laws. Kirchoff's laws. Kirchoff's laws. What are these Kirchoff's laws? We have two Kirchoff's laws. First one is Kirchoff's current law. The second one is Kirchoff's voltage law. So Kirchoff's current law is also called as junction law. Kirchoff's voltage law is also called as loop law or mesh law. So what this Kirchoff's current law tells is you can state this in two different ways. If you have a junction, at the junction, if two or more circuit elements are meeting, like this resistors to be considered, so that if current I1 is coming here, I2 is coming, and it is going here, going out as I3, I4, and I5, then Kirchoff's current law says at a junction, at a node or junction, sum of the currents approaching the junction is equal to sum of the currents leaving the junction. This is called Kirchoff's current law. Sum of the currents approaching the junction is equal to sum of the currents leaving the junction. This is called Kirchoff's law. Or you can also say algebraic sum of all currents at a junction is equal to 0. This can be expressed as sigma I, where I goes from 1 to n is equal to 0. This is mathematical expression for Kirchoff's current law. Algebraic sum of all the currents at the junction means the inward currents will take positive, outward currents will take negative. So if I write I1 plus I2 minus I3 minus I4 minus I5 equal to 0. So mathematically you can also express this as I1 plus I2 is equal to sum of the currents approaching is equal to sum of the currents leaving. That is I3 plus I4 plus I5. Or you can also write it as I1 plus I2, bring it here, minus I3 minus I4 minus I5 is equal to 0. That way I say, either way it is similar. Both can be called as mathematical expressions for Kirchoff's current law, and in general you can write this. And here you have to remember that Z is a consequence of conservation of charge, or it is based on law of conservation of charge. It is based on, or it is a consequence of law of conservation of charge. Conservation of charge. Conservation of charge. Is it clear? Whereas mesh law or Kirchoff's voltage law, Kirchoff's voltage law says algebraic sum of all potentials in a closed loop is equal to 0. Closed loop. You should have a closed loop. So write down Kirchoff's voltage law next. Kirchoff's voltage law. Algebraic sum of all potentials. We can use different words. Voltage, potentials, or potential differences, or potential drops. Any words we use. Okay. Algebraic sum of all potential drops across every element, or potentials across every element in a closed loop. In a closed loop is equal to 0. Is equal to 0. It is given by, mathematically it is given by sigma of delta V I, where I is equal to 1 to n. Or you can say delta E I also can say, or you can say E is equal to 0. Algebraic sum of the potential differences or potentials. Or you can also write it as sigma of Vi is equal to, where I goes from 1 to n is equal to 0. Either any sequence we use. Okay? This is Kirchoff's voltage law. Then I have to remember that Kirchoff's voltage law is the consequence of the law of conservation of energy. This is based on law of conservation of energy. It is based on law of conservation of charge. Sorry, energy. Based on the law of conservation of energy, or is a consequence of it. And obeys that. Okay? This is briefly about Kirchoff's current law and voltage law. Once you know this, you should remember the sign convention used in a loop or in a circuit. The sign convention for resistors and cells. By making use of the sign conventions, you can work out different circuits. So write down next subheading: sign conventions. Sign conventions. Sign conventions. So first, we will consider 4 points under this sign conventions. We can consider only 4 points under this sign conventions. Okay. First one is let us consider a resistor. And before getting into the sign conventions, you have to write a note. That is, current always flows from higher potential to lower potential. Current always flows from higher potential to lower potential. Higher potential to lower potential. Write down higher potential to lower potential. Lower potential. Copy it everyone. Higher potential to lower potential. Why we need that? We will understand that. So if you observe the sign conventions, so the first point, if you have a resistor of resistance R, this current I is flowing, let us say from point A to point B. You follow it. And if current is flowing, what is that? Current always flows from higher potential to lower potential. means this junction A, left side of the resistor will be taken as higher potential, right side will be taken as lower potential. If current is flowing from A to B means this has to be flowing from higher potential to lower potential. This is at higher potential means it will be represented with positive sign. It is at lower potential, it is represented with the negative sign. Whereas if that means we are going like this, then potential difference delta B, what is it is taken as we are going from positive to negative and minus 10 million. Negative minus IR is the potential difference. This is what you have to take if you are going in this direction. Whereas if you have the same resistor, second point, in this current I is flowing from this resistor of resistance R, this is A, this is D. Okay? But we are coming in this direction, in the loop. So as current is flowing here, this is positive, this is negative. But when we are coming in this direction, potential difference delta V will be taken as we are coming from lower to higher potential. Current is going from higher to lower, but you are coming here. This arrow says you are going from plus to minus or higher to lower, but you are going from lower to higher, that means minus to plus. So plus you have to do. Plus potential difference will be taken as delta. So if you go in the direction of current, potential difference will be taken as negative. If you go in the opposite direction of current, you have to take the potential difference as positive. Is it clear? For a resistor. Whereas for a cell, if you have a cell, they have EMF E, and here the current I is entering into the cell. So that this is point A, terminal A, this is terminal B. Then, when you are going from A to B, here to here, or whatever it is, you can take a range only. This is A, this is B. Then, for always for battery, you have to take the bigger line is higher potential, smaller line is lower potential. Is it okay? So, we have irrespective of this current direction, in this case of cells, you have to say that if you are going in this direction means potential difference delta V is equal to, that means you are going from plus to minus. So minus E will be the potential difference. Got it? Negative potential difference will be there. Whereas the fourth case, if you are going like this is the cell with higher order potential V, you are going from A to, so if you are going from B to A, the opposite direction. Even the current is whatever the direction of current. So then you have to take this is negative, this is positive. The potential difference will be equal to plus. This is how you have to take the sign conventions of potential differences across resistors and the cells while dealing with circuits. Okay. Now let us try to work out few questions based on this circuit theory. Then you can go ahead with applications of these Kirchoff'S laws like the Wheatstone'S Bridge and meter bridge, etc. Okay. First, let's take this example. Okay. These sign conventions are clear, everyone? Yes. Copy. Right. These are very important. If you can't follow this, you cannot understand circuit theory. Next, let's take one example, simple example. Find the current through each resistor in the circuit, right? Find the current through each resistor in the circuit. Find the current through each resistor in the circuit. We have a resistor here, and here a cell of EMF 2 volts and a resistor, and here another cell and resistor. It is 3 volts and 2 ohms resistor. Here we have again one more cell and resistor. This is the current. This is 2 ohm. This is 2 volts only. And here we have a cell. We have a cell having 5 volts across this diagram. We find the current through each resistor. Find the current through each resistor. This is also 2 ohm, 2 ohm, 2 ohm, 2 ohm. Got it? Yes. So, how to find? In such cases, what you have to understand is, here we have one more resistor reference here. Okay, that is a very simple circuit without this resistance also. Then you can apply to the other circuit having more number of elements, circuit elements. In these cases, what you have to do is, you can apply Kirchoff'S laws by considering closed loops. That is one way of simplifying this approach. Another way is by using the point potentiometers. You can say EB potentiometers. By using potentiometers. According to this potentiometer, the point potentiometer, let us first identify the section which is having only a cell, if at all there is a only single cell. If not, you have to use another different way, different approach. In this case, mark the lower potential as 0 volts and higher potential as V volts. V here is nothing but 5 volts. So you can take this as 5. Higher potential should be 5 volts. Lower potential should be 0. Then, so here the potential difference of the cell is 3 volts. That means higher potential is, this is connected to this means higher potential should be 5. So what should be the lower potential? So that potential difference of this should be 3 volt. You have to identify. Yes. So this is for making this little simplified. Let us consider only 2 cells and 2 circuits, 2 resistors. These let me erase and will give you a simplified form. Then in the next stage we will take it a different way. So here this is connected by a connecting wire, this is connected by a connecting wire. Is it clear? Connecting wire. Now what you have to understand is this is 0 volts, and in this section it is connected by a connecting wire. We also call it as a short circuit. What is this? Short circuit. If you have a short circuit, then potential available will be same. This is 0, this also will be 0 only. This also will be 0 only. Are you following? So now this is the higher potential of this battery. It is 0. What should be lower potential? So that the potential difference should be 2 volts. So higher minus lower is 2. Higher is given as 0. So you have to take we don't know what is lower. Let us take there some x. So 0 minus x is equal to 2 volts. So what will be x? Minus 2 volts. So this will be minus 2 volts. Is it clear everyone? So whenever you have given a battery with a potential means, so that is the potential difference of the 2 terminals of the cell. So we also have to remember that higher potential always doesn't mean it should be positive value. Even here higher potential can be negative value also. But lower potential should be less than that. That is the meaning of it. Okay. So next, this is for this higher potential is 5 volts. What should be the lower potential? So that potential difference will be 3 volts. So you can say higher potential is 5. Let's say lower potential is some x. 5 minus x is equal to 3 volts. Are you following? So that what will be x? Take x this side, it becomes plus x. You bring it here, then 5 minus 3 becomes 2. So this will be 2 volts. Got it? Higher potential is 5, lower potential is 2. So 5 minus 2 is 3. That is the potential difference. Next, this is 0. So this is connected by connecting wire or a short circuited wire. So this is also 0. So this is 2, this is 0. Got it? Now, what we are asked to find? Find the current through all the resistors. How many resistors are there? Only 2. Or you may also say, what is the current to each branch? Okay, here only 2 resistors are there. So you can see this is first resistor. R1 equal to 2, this is R2, this is R2 also equal to 2 only. So we have to remember from Ohm's law that current I is equal to V by R, or potential difference by resistance. From Ohm's law, we know that I is equal to V by R, or delta V by R. So here, delta V for the first resistor, you say, so from this you can say VI1 is equal to delta V1 by R1. Potential difference across first resistor, this one. For the resistor, what is potential difference? So this is one is minus 2 volts, another is 5 volts, which is higher here, 5. So 5 minus 3, sorry 5 minus, this is higher potential, this is lower potential. Are you getting this? Yes or no? So what you have to take is higher minus lower. Higher is 5, minus lower is minus 2. So you have to take minus of minus 2 by resistance of this is 2 ohm. So it is 5 minus of minus is plus 5 plus 2 is 7 by 2 is equal to 3.5 ampere. Is it clear everyone? 3.5 ampere. Then what is the current through the second resistor? I2 is equal to delta V2 by R2. What is the potential difference across second resistor? Higher minus lower. Higher is 2, lower is 0. So it is 2 minus 0. Its resistance is 2 ohm only. So 2 minus 0 is 2 by 2. Is equal to how much? 1 ampere. Is it clear everyone? Means current always flows from higher potential to lower potential. For the resistor, this is higher, this is lower. So current flows in this direction. Is it clear? That means current is flowing here in this direction. Here, this is higher, this is lower. Current is flowing in this direction. Yes? So that means this is your I1, this is your I2. So These were coming here and combining and going to the this is fine. Yes. It means this will be your I. This is your I. It is divided into I100. So if you are asked me to find what is the current in each section, to each resistor you are asked me. Each section is this section and this section and this section. What is the current in this section? What is I? What happened? What is I? I is equal to I1 plus I2. So what is that? What is that? 4.5 ampere. So each section you can calculate what is the current by making use of this kind of simplification. Right? Yes, right then. Next, copy. Right, next question.
Sir, higher potential to lower potential. 5 volt set.
5 volt? This, yes.
Lower potential.
This is lower, this is higher. So from higher it is coming. So here you can say why can't from here to here, higher to lower, from here to here you have to go like that. For a cell, this is higher potential, this is lower potential. Current will flow from, if current is a resistor or some element, current will be drawn from the battery. Current will be discharging, you can call it a discharging cell or drawing the current. If current is flowing into the cell means some external source is giving current, it is giving to the cell, so it is charging condition. So drawing the current means always current will be drawn from higher potential. So inside it will go from here to here. Okay? But here outside it will go from higher to lower, higher to lower, outside circuit, higher to lower. Alright? Right. Next. Is this okay? So this kind of questions we try to go through some other questions. Next. 4? In the timing. Yes, we'll see. Once. So what? How to find? What you are asked to find? What is energy consumed? Energy consumed, right? Yes. See. So this is briefly about what you call combination of cells and the questions based on the cells and with resistors called circuit theory based questions we will call them as circuit theory based questions. If you have a single cell in a section, this is okay, fine, very simple. Whereas if you have a resistor also in one of the sections, then it will be a little different. And how to deal with them? So let us see. So another simple question. Then we will try to understand. We will try to work out some other questions. What is the time? You have time? Already 4 o'clock. You continue till 5 o'clock? Anyway, you are sleeping, right? Sleep. Yes? Why is the lunch ready? Sunday. What will you do after doing master? Okay. Okay then. So I will wind up in 5 minutes. I will give you one simple question. Did I bring anything? So let us work out one more simple question. Right. Yes, note down this. Find current through each resistor. Find current through each resistor. Let us say in the figure shown, we have a resistor here and then a cell, and here one more resistor and a cell connected to this. Now this cell is connected to another resistor and this is connected to the connecting wire. And these are connected by connecting wire. Now, these are connected by connecting wire. Here, one more cell along with the resistor is connected in this section. So that these resistors are given as 2 ohm, 2 ohm, 2 ohm. All are 2 ohm resistors. And this cell is having 2 volt potential. This is having 10 volts potential, and this is higher potential. This is lower potential. This is higher, this is lower potential. So that this is 4 volt resistor, 4 volt potential. What is the current through each resistor? Is the question. What is current through each resistor? Here, so if you have a single cell in any one of the sections, then it is very simple to give the what you call potentials. But here we don't have such things. So you have to use Kirchoff's current law. According to Kirchoff's current law, what is that? The algebraic sum of all the currents at the junction is equal to 0. Let us consider this is the junction, the main junction. From here, let us say current I1 is flowing here, current I2 is flowing here, current I3 is flowing here, current I4 is flowing here. Vector sum of all the currents is equal to 0. Vector sum of all the currents is equal to 0. Means I1 plus I2 plus I3 plus I4 plus I4 only, right? I4 is equal to 0. But we know current is nothing but what? Potential difference by resistance. So current across this is nothing but potential difference across this by its resistance. Resistance is we want potential difference. For that purpose, what we consider is, let us consider this potential is x. Let us consider this potential is some x or v or I mean is any symbol you can give it to it. So okay, some v, some unknown potential. Let us take it as some v. Unknown potential v. So if you know what is this potential, then it is easy to find out. Okay. So to find this, let us try to write expressions for this. When current is flowing here, let us say this is lower potential, this is V, and let us consider this is for this battery. For this battery, higher potential is V, lower potential is something, so that potential difference should be 2 volts. Potential difference should be 2 volts. Then what should be this? Let us say this is some x. V minus x is equal to 2 volts means what is that x? X is equal to V minus 2. So you have to take this as V minus 2 volts. Is it clear everyone? Right. Here we have a battery here, right? Let us consider this lower potential is 0 and this higher potential is 10. Okay? Lower potential is 0, higher potential is 10. So 10 minus 0 is 10 volts. Now this is connected by a connecting wire. Let us take this as 0 volts. So for this resistor, this potential is nothing but V minus 2 volts. V minus 2 volts and this potential is 0 volts. Right? And for next for this resistor, higher potential is V, so another potential is 10. So if you know this V, you can find this current. If you know this V, you can find this current. For this again, this is V, what is this potential? Here this is 0 means this is also will be 0, connecting wire. But this is lower potential. If lower potential is 0, what should be higher potential? So that potential difference should be 4 volts. Let us say it is x. X minus 0. What is that? X minus 0 is equal to 4. So what is this? 4 volts only? 4. So if you this for this resistor potential difference is V minus 4. Difference between them. If you know V, you can find it out. And this is 0 means this is connecting wire. This also will be 0. So likewise we will get potential difference for every resistor if you know V. So for that purpose, let us let us try to make use of this Kirchoff's current law. According to this, current across the first resistor is delta I1 is equal to delta V1 by R1 plus delta V2 by R2 plus delta V3 by R3 plus delta V4 by R4 is equal to 0. Got it? Next step is you can mention this as for first resistor delta V1 is potential difference between these two. This is 0 and this is V. So V minus 0 is potential difference. V minus 0 by resistance 2 gives you current. So this can be expressed as V minus 0 also implies V minus 0 by 2. That is I1. I2 is this one V minus 4. Let us take it as this is higher. Take it the direction of current is this. So higher to lower. V minus 4. V minus 4 by resistance is 2 only. Plus for this V minus 10. V minus 10 by 2. For the fourth one, this is where is fourth one? This is the fourth one. So it is V minus 2 minus 0. So it is plus V minus 2 minus 0 is V minus 2 only by 2 is equal to 0. Is it clear? On simplifying this further, because in every denominator we have 2 only, right? Take LCM 2, then you will simplify. V, all plus V's 1, 2, 3, 4. 4 V's minus 4, minus 10, minus 2. How much? Minus 16 is equal to 0. So 4V is equal to 16 or V is equal to how much? 4. 16 by 4 is equal to 4 volts. You understand? This is 4 volts. Now we can from that we can find out what is that separately. I1 I2 I3. I1 is equal to delta V1 by R1. What is delta V1? V minus 0 by 2. It is V by 2. What is V? 4 by 2. It is equal to 2 ampere. Is it clear? Yes. And what is I2? I2 is delta V2 by R2. It is equal to delta V. This is I1. This is I2. V minus 4 by 2. V minus 4 by 2. It is, what is V? 4. 4 minus 4 is 0. 0 by 2 is 0 volt, 0 ampere. That means, where is second resistor? This one. To this, no current will passes. So this is no current passes. So it is a dummy. Okay. Next, I3. I3 is equal to delta V3 by R3 is equal to delta V3 is V minus 10 by, what is that? R3 is how much? R3. So V is how much? 4. 4 minus 10 is minus 6 by 2 minus 3 ampere. What is this minus? Direction is reverse. Negative sign says that direction is reverse. Means here that current is going in this direction. Why? V is 4, right? This is 4 is higher or 10 is higher? 10 is higher. So current is from higher to lower. So that means current will flow in this direction. And we have taken that way. So we are getting negative sign. That means current is going in opposite direction. That is the meaning of this. You can write down here. Negative sign says current flows in opposite direction. This current flows. That is I3 flows in opposite direction. Next, I4. I4 is 4 minus 2 by 2. V minus 2 by 2. It is equal to, sorry, by 2. 4 minus 2 is 2 by 2. It is equal to 1 ampere. This is the current in each resistor. Got it? So try to work out these kind of questions. And in the next session, we will try to discuss briefly about what is that? Wheatstone bridge, meter bridge, and potentiometer. So we have only one session. In that we have to discuss these things and gravitation. Yes? Gravitation also have to finish. Can we? 40 minutes we have to finish like that. So we have to take one more extra session. So this is actually we have given directions to finish everything in this, but we are taking so many extra hours to help you guys. But you guys are not realizing that. Simply you guys are wasting time.